This is KBYP with a second video about the balanced modulator and mixer to explain the diode physics that are necessary to then select replacement mixer diodes for the TR3 and TR4 balanced modulator. And I realized from watching these videos on the TV, I can't see the video description where the email is. K8BYP with underscores between the characters at IEEE.org if you want to email me. There's a symbol for a diode as a component. See the circle? The circle is an envelope. Below it is a symbol for a diode junction, which we must look at to understand diode operation. A diode is a PN junction. That illustrates a piece of positively and negatively doped materials not put together. Then below that, when they're put together, there's a positive piece on the left and negative on the right, and what's called a potential hill or a barrier in between, a no man's land. That barrier is what causes the diode action. That barrier implies that a certain voltage is necessary. See the voltage across the width of the barrier? In order for current to flow. And majority carrier flow goes from being electrons goes from the right to the left, and the negative out to positive. That's what we call forward biased. That's described as a potential hill in semiconductor theory. Hill implies that energy inputs needed to overcome it and allow current flow. When those two pieces are put together, like such, then connecting wires must be bonded to it, and that forms a diode unit. What's happening inside with the no man's land magnified and illustrating the two wires with their bonds against the PN material is that at low voltages, just enough to barely turn the diode on, the electrons, the current flow takes a path here close in. As the current flow increases, the current flow increasingly spreads across this junction, where at higher current levels it may be way over here, which implies current flowing through the entire barrier region. So at low currents, this defines a small cross-section through which current flows, and at high flows it's flowing through the entire cross-section, and that implies a change in resistance which is non-linear. And that, the movement of this current spread, is essentially what accomplishes mixing. It's a non-linear feature. That doesn't happen in vacuum tubes, because vacuum tubes are not solid state, they are electron coupled, and no such thing exists for the most part. It may exist in a small way at the elements, but probably not enough for mixers, which is kind of, I think, sort of the reason this couldn't be done with vacuum tubes until semiconductors came along. When there's sufficient current flow, the diode conductivity tends to become linear, and that defines a linear region in which mixing does not occur. The data we look for in a data sheet is called the IV curve. Simplified from Ohm's law, V over I times R. If we want to find R, we divide I into V. That's IV. The IV curve will look something like this. If it's a linear graph, I made a slight error in drawing it, but in an XY graph, there will be a nonlinear conduction region down here in which mixing occurs, and then at high enough currents, when most of the junction is conducting, that will level off and become linear. At some very low current and decreasing, there won't be enough energy to overcome the hill, so it'll drop straight off. And this graph tells us a great deal. There are three regions of the graph and slopes to be concerned about. At the far left, no conduction region, where the curve just drops straight off to the x-axis. The nonlinear portion, which I kind of drew inaccurately, but that's where the mixing occurs. And then in the linear region, no mixing. The no conduction region is important because with a modulating signal that looks like the sine wave on the left, that is a continuous function. It starts at the zero line, goes up to maximum, back to zero, down to minimum, and back. What that no conduction region does is essentially blanks out that signal at zero crossing. So there are gaps in it, and the higher that potential hill, the further up on that modulation envelope that the modulation voltage will have to be to begin conduction and begin mixing. That's why we can't use ordinary silicon rectifiers. They have a forward drop of generally 0.48 to well over a volt. And that contradicts this balanced modulator theory, which says that the carrier level must be relatively high and the modulating signal be relatively low to be able to separate out the modulation signal. So what that implies is that we need diodes with a very low forward voltage drop. We need diodes with a low V sub F forward voltage on the range of, and you won't see this on a data sheet so much, but I've measured it 10 millivolts to about a quarter of a volt, maybe 3/10 of a volt. That's typical for germanium and Schottky barrier diodes. Germanium's ancient history. Germanium has problems. It's unstable. So today we use Schottky barrier diodes, or SBRs, barrier rectifiers. They have very low forward voltage drops. At very low currents, that drop might be 25 millivolts. So that means that almost all of the modulation envelope can be devoted to mixing. And it also means that if we know where the noise floor is in the modulation signal, we might also choose a rectifier that can clip that out. So there's an advantage to not having it too low. The mixing range of the diode must be sufficient to allow sufficient carrier throughput and sufficient modulation throughput to put enough signal out of the sideband filter into the mixer to be able to generate enough signal downstream to the PA driver and to be able to drive the PA stage to full conduction. Otherwise, the power output from the transmitter will drop. So this is rather complicated and difficult to measure and really difficult to do on paper. It should be fairly obvious that the diodes must be very carefully matched. And I'll show you here in a second a data sheet from Infineon for one of their diodes that list matching somewhere between 10 and 20 millivolts, which is very, very good. I've measured far more than that difference in these original diodes in a Drake with a diode test. And I'm going to stop this video here at video 2, and video 3, balanced modulators and mixing, will be showing the diode characteristics and onward. KBYP.